Let us consider a case on hypergeometric distribution, which is a discrete type of distribution wherein the random variable x is defined in terms of parameter m, n, and capital N of hypergeometric distribution, where capital N is the sample size, n is the total number of draws, m is the total number of successes. Since discrete distribution, we have a probability mass function which is defined as mcx into capital N minus m c n minus x by capital N c n, where x varies from 0, 1, 2, so on till n. Now let us calculate the central tendencies such as mean and variance using expectation method, where expectation of x is given by x into probability mass function, which is summed over x, which varies from 0 to n. Substitute the probability mass function and simplify it. This simplification takes some time. Well, at least you can appreciate the characters that are written on the screen. Obviously the beauty, I mean. Now, after cancelling the factorizations, we'll get mn by capital N into summation of m minus 1 factorial by m minus x factorial into x minus 1 factorial multiplied by capital N minus small m factorial by capital N minus small m minus n plus x factorial into n minus x factorial, the whole divided by capital N minus 1 factorial by n minus small n factorial into n minus 1 factorial. This whole thing is obviously summed from x equals to 1 to n. Here we have a property where summation of m minus 1 c x minus 1 into capital N minus m c n minus x divided by capital N minus 1 c n minus 1 for x from varying from 1 to n is 1. This is because the probability mass function f of m minus 1, n minus 1 and capital N minus 1 for hypergeometric distribution is 1. Hence we get the estimate of x as mn by capital N, which is mean. Next, let's move on to variance, which is given by estimate of x square minus mean square. So estimate of x square can be written as estimate of x into x minus 1 plus estimate of x. Let us calculate the value of estimate of x into x minus 1, which is equal to x into x minus 1 into probability mass function, which is summed from x equals to 0 to infinity. Substitute the probability mass function and simplify. So here we have changed the limits of x equal to 0 to 2. That's the point to be noted, because we cannot have negative figures in here. There are many possibilities of error over here, so one needs to be careful while simplifying it. As I said earlier that this is a cumbersome process, please keep appreciating the beauty of the letters. So we get estimate of x into x minus 1 as m into m minus 1 into n minus 1 by capital N into n minus 1. Now we substitute this value to get the estimate of x square So this plus mean will give us estimate of x square, which is mn by capital N into m minus n plus capital N by capital N minus 1. Now we calculate the variance. Variance, as I told earlier, is defined as estimate of x square minus mean. Estimate of x square is what we got in the initial step. Previous step. So simplifying this further, taking mn by capital N common, normal LCM simplification after this. These type of hypergeometric distributions are different from binomial distributions, where binomial distribution describes the probability of successes in n rows with replacement, whereas here there is no replacement. In the end, after simplification, we get variance as mn by capital N into 1 minus n by capital N multiplied by 1 minus small m by capital N. Now let's move on to moment generating function, which is moment generating function is defined as summation over x equals to 0 to n for e power tx multiplied by the probability mass function, which over here is mcx into capital N minus small mcn minus x divided by capital N cx. We are separating to the terms over here. So while separating, now we get 1 as one term and plus summation of xt power r by r factorial into mcx multiplied by capital N minus mcn minus x divided by capital NCN, which has double summation, first x which is for x equals to 1 to n and the other is for r equals to 1 to infinity. We are introducing a new term capital F of r, which is the sum of first r coefficients of hypergeometric series. So in this way we calculate center tendencies for hypergeometric series and also a moment generating function.